All right, in this video, we're going to look at question 2 on the worksheet that says, consider the unit square S, which is the product of the interval 0 to 1 with itself in the UV plane. Sketch the image of S under each transformation below. Okay, so we have this unit square S in the first quadrant of the UV plane, and we're going to apply various transformations to this square and describe the corresponding image regions over here in the XY plane. And for part A, our transformation t is described by the equations x equals 2u and y equals 2v. So let's first see what this transformation t does to the boundary of this square. So we'll go ahead and consider first this bottom edge in green where u varies from 0 to 1 and v is equal to 0. And so the fact that v is constant 0 will imply that y being twice v would be constant 0. And letting u vary from 0 to 1 implies that x being twice u will vary from 0 to 2. Okay, so these conditions are describing this interval along the x-axis. Okay, and I'll go ahead and label this bottom edge is 1 here for S, and its image is 1 prime. And what we're seeing here is that this transformation t is just dilating this unit interval along the u-axis by a factor of 2 to give us this interval here along the x-axis. All right, so now let's go ahead and look at this edge in red. Here, v varies from 0 to 1, and u is constant 1. So u being constant 1 will imply that x being twice u will be constant 2. And v, this varies from 0 to 1, so that's going to imply that y will vary from 0 to 2. So these conditions describe that edge. All right, and then moving along, we have this top edge for S, and exact same idea as the others. So the fact that v is 1 will imply that y is 2, and u varying from 0 to 1 will imply that x varies from 0 to 2. So that's going to give us this edge. And then this left edge here for S, where v varies from 0 to 1 and u is equal to 0, that's going to tell us that x is constant 0 and y varies from 0 to 2. And so that's going to give us this edge right here. Okay, so the boundary of our square S is mapped to this boundary of the image region. And so altogether then, the image is this square with side lengths 2 in the first quadrant in the xy plane. Okay, and I'll label that that region R. Okay, and this notation T of S, much like function notation, is just saying that R is the image of the square S under the transformation T. Okay, and we see here that T is just simply dilating lengths by a factor of 2. Okay, so with that in mind, it's a little preview of some things to come. If I were to consider a differential rectangle in the square S, so side length du and side length dv, okay, each one of these side lengths, du and dv, will be mapped to lengths twice as long. Okay, so this differential rectangle will get mapped to this differential rectangle with side lengths dx and dy, where dx is twice du and dy is twice dv. And so for the area element, which is dx dy, this will then be twice du times twice dv, which is 4 times du dv. Okay, so put another way, if the transformation t is dilating lengths by 2, it will multiply areas by 4. Okay, and this 4 is what's known as the Jacobian of the transformation t, and it's just the area distortion factor of that transformation. Okay, so more on all of that to come as we get into integration with substitution. All right, but for now, let's go ahead and look at part B. So here we're looking at the transformation where x is 2u and y is 4u plus v. So again, we'll just start by looking at what t does to the boundary of our square. And here, for this bottom edge in red, u varies from 0 to 1 and v is 0. So the fact that v is 0 will imply that y is equal to, well, 4u. Notice v only shows up in the expression for y, but we also know that x being 2u implies that u is half x. So y being 4u then says that y is equal to 4 times half x, which is 2x. So in other words, the condition that v is constant 0 implies that y is 2 times x. Okay, now letting u vary from 0 to 1 will imply that x being twice u will vary from 0 to 2. So these two conditions are describing the portion of the line y equals 2x as we let x vary from 0 to 2. So in other words, this bottom edge here in red is going to get mapped to this line segment here, which is just that y equals 2x, just restricting x between 0 and 2. Cool. All right, so then how about this edge in green where v varies from 0 to 1 and u is equal to 1. Okay, so now if we fix u to equal 1, then this is going to imply that x being twice u will be constant 2. And it also says that y will be 4 times u, which is 1, plus v. So in other words, y is equal to 4 plus v. And now as we let v vary from 0 to 1, that's going to imply that y will vary from, well, 4 at the low end to 4 plus 1, which would be 5 at the high end. Okay, so our two conditions here really are that x is 2 and y is varying from 4 to 5. So these conditions describe this little line segment here. So it's the portion of the vertical line x equals 2 as we let y vary from 4 to 5. Cool. All right, moving along. We have this top edge. So there u varies from 0 to 1 and v is equal to 1. Okay, so if v is constant 1, that's going to imply that y is equal to 4u plus 1. But again, we know that u is half x, so this would be 4 times x over 2 plus 1, which is equal to 2x plus 1. Okay, so in other words, v being constant 1 says that y is equal to 2x plus 1. And now letting u vary from 0 to 1, this will imply that x being twice u will vary from 0 to 2. So these conditions are describing the portion of the line y equals 2x plus 1, which is just this red line shifted up 1, and we're again restricting x to be between 0 and 2. So we're describing this line segment right there in purple. All right, great. And then for our leftmost edge of S, where v varies from 0 to 1 and u is equal to 0, okay, very similarly now, sorry, kind of leaked into the room there. So if u is constant 0, then we're saying that x is constant 0, and y would be, well, 4 times 0 plus v, so it's just going to equal v, and we're letting v vary from 0 to 1, so y will vary from 0 to 1. Okay, so you put all that together, and we're really saying that x is 0 and y varies from 0 to 1, so we're describing that line segment right there. Okay, and so then the image in yellow here is going to be this parallelogram you see, and the distortion of area here is a little bit more complicated than the last example. But in the next couple videos, we will unpack exactly how we can go about finding that area distortion factor for a transformation like this. Cool. All right, so let's now go ahead and move on to the last one. This is part C, taking out all these layers here. So here's C. We have that x is equal to u minus v all over the square root of 2, and y is u plus v all over the square root of 2. Okay, so starting with that bottom edge, where u varies from 0 to 1, v is 0. So let's see, if v is 0, what are we going to get? Well, x then would be u over the root of 2, and y would also equal u over the root of 2. Since they're both equal, x and y are both equal to u over root 2, this implies that x and y are the same. Okay, so the condition that v is 0 says that we're going to get a portion of this diagonal x equals y, and the fact that we're letting u vary from 0 to 1 will imply that x and y, being u over the root of 2, will vary from, well, 1 over the root of 2. Okay, so these conditions right here says that the image of this bottom edge under the transformation t will be this line segment, which again is just the portion of the line y equals x as we let x and y vary from 0 to 1 over root 2. Okay, so then for this next edge in green, v varies from 0 to 1, u is equal to 1. Okay, so very similarly now, we have that u is 1. So we have that x is 1 minus v over the root of 2. And y is equal to 1 plus v over the root of 2. Okay, so we could go ahead and solve for v in one of the equations and then substitute in. That'd be perfectly fine. But I think it's a little bit simpler here, just given the forms of these expressions for x and y, to add them up. If you add x and y here, notice the minus v over root 2 and the positive v over root 2 are going to cancel out. And I'm going to wind up getting, well, 2 over root 2, which is equal to root 2. So I'm really describing a portion of this line, x plus y is equal to the square root of 2. And we're letting v vary from 0 to 1. Okay, so since, say, x is 1 minus v over the root of 2, what will that say about the bounds on, say, x? Well, for x, if v were 0, then this would be just 1 over root 2 at the high end. And if v were 1, x would be 0. So x is varying from 0 to 1 over root 2. So we're describing now the portion of this line, x plus y is the square root of 2, as we let x vary from 0 to 1 over the square root of 2. Okay, so that's going to describe this line segment there. Okay, and although I didn't put it in the figure, this height right here, which would just be the y-intercept of this green line, x plus y is root 2. This would be up here at root 2. Okay, now go ahead and just do the same thing, but for these other edges. Okay, and you can go ahead and I'll leave the work to you. It's a good exercise. You're going to wind up getting for this third edge, this line segment here. Okay, and then you're going to get for this fourth edge, this left edge here for S, it's going to get mapped, as you might suspect, to this edge right here. Okay, and so our image region here is this, it's a square. It's actually a unit square. In fact, it's just this unit square rotated 45 degrees counterclockwise. Okay, so if you've taken linear algebra, you may recognize this transformation as a rotation of the xy plane. That's exactly what this thing is doing. It's just simply rotating there. Okay, so that is a good place to stop. This gives us a lot to go off just in terms of how to think about describing the image of various regions under transformations. In the next problem, we're going to look at some more examples where the regions are not necessarily going to be bounded by straight line segments. So in other words, we're going to be looking at some nonlinear transformations. So I'll see you there. Thanks.